It shifted. Okay.
Okay. Yeah, so that's why. So in that sense, the date is even more important than the topics. Like, even if I don't finish all those topics to give it, I'm giving you a test on whatever we've covered up to that point.
Gotcha.
So the first test date is definitely firm.
Okay.
Because at that point, you should have like 5 or 6 quizzes and a test to really understand how well you're doing. And so the following week, if you need to make decisions about cutting anything, you'll be able to make an informed decision. So that's the reason. And remember, there's a meme where it's like all the science departments and the math departments get together like, let's create a test on the same day. Okay, break. It's not really like that technically, but it just happens that way because that date is important. So everyone puts a test the week before. So at that weekend they can have time to grade. So they give you at the beginning of the following week. So by the time, I don't remember when is the specific last date to drop. It's in the syllabus I put on the, it's in the calendar I put on the syllabus, but it's probably like the Tuesday or Wednesday of the following week, something like that. Anyway, so yeah, limits as a topic, we're pretty much done with. Not that we're done with limits, we will be seeing them, but they're not going to be the focus. We're kind of going to be segueing today, and we're going to talk about the rate problem. Now, at some point, earlier in the semester, I think in lecture 2, I told you that calculus was really broken up into 2 branches. There's differential calculus, there's integral calculus, and the point of differential calculus was to solve the rate problem. Okay, so this problem can be stated in various ways, but essentially, within some context, you want to figure out how fast some quantity is changing. Usually it's in terms of maybe a travel object, and you know you're tracking its distance over time, and you just want to know at some specific point in time how fast was that object moving. So it's often quoted in the kind of distance slash velocity slash acceleration. What was that word? Context. Okay. So this was the rate problem, something that was very important to be able to solve because things change, and knowing how fast they change will allow us to plan for the future or develop anything that we need to develop to solve problems. So figuring out how fast something moves was a very important thing. So let's do an illustrative question or situation or statement, okay, to kind of illustrate the thought that led to the solution of this problem. Okay, suppose we're tracking an object, and this is like the 3rd time I'm saying this semester. I don't remember if I told you guys, but suppose we were tracking an object. And to simplify matters, let's assume it's moving at a constant rate of speed, so that there are no changes in its speed at any point in the journey. So we're just making things simple. And you find the following. Okay. So here's the object. You're tracking its distance over time. For argument's sake, let's say you're measuring time in hours, measuring distance in miles. And so, okay, so you start tracking the object at what you call position 0 at time 0, and you're seeing how far it goes after a while, right? So you can track it, after 1 hour, after 2 hours, and it just keeps going. But you notice that after 3 hours, the object is now 150 miles away. Okay. Traveling at a constant rate of speed, so a straight line is going to be the best way to track that distance. After regular intervals in time, there will be a regular change in distance. That's what it means to be a constant rate of speed. It's not speeding up or slowing down. And so now here's a question that, I mean, if you haven't been in calculus before, it might seem like a strange question to ask, or why would it be meaningful? But the question is, you notice this is a straight line. There are some things you might want to know about a straight line. So specifically, you might want to ask, what is the slope? What is the slope of this line? Huh? 50. The slope is 50. So we know slope as rise over run. So it rises by a distance of 150 over a time of 3. So you can, I mean, you could do it the long way, 0, 0, and this is 3, 150, y2 minus y1 over x minus x1, or you can just notice that rise over run would give you 50. The answer is 50. Now here's that question, a follow-up question. What does that mean? What is that 50? How does that number relate to this situation? What is that number telling us about this situation? Yeah?
Every hour it moves 50 miles.
Okay. Now, let's get a little bit more specific here. If we were to find the slope, which is y2 minus y1 over x2 minus x1, and let's say we start to decide to be physicists for a while, so we're even keeping track of the units to our number here. Yes, you can think of it as moving 150 miles over every hour, moving 50 miles every hour, but specifically, what you just computed was 150 miles minus 0 miles over 3 hours minus 0 hours. So in other words, you would end up with 50 miles over hour, right? Another way of writing that is 50 miles per hour, right? Now miles per hour, as you might know, is a traditional way of measuring velocity, right? Velocity is a very technical term. Velocity has direction built in, but people might think of this as a speed or a velocity. The velocity and the speed would actually be the same quantity here. But it's worth noting that that was an interesting thing to notice. Tracking the distance of an object over time, in the event that it's traveling at a constant speed, the slope of that line actually tells you how fast the object was moving. Now remember what the rate problem was trying to figure out how fast something is moving. Now it turns out if you're tracking a distance over time, hey, the slope seems to be a pretty convenient quantity for doing that. So that is the genesis of the thought that helped us to solve the rate problem. There is a connection between slope and speed. There's a connection between slope and quote-unquote rate of change. The slope of something that you're tracking over some distance tells you how fast that object is moving over that distance. And thus it began. That was in the beginning. That thought was the thought that sparked the solution to this problem. Right? Following this thought to its logical conclusion, differential calculus. So now, of course, there's an objection. Not all things move in a straight line. Not all things move at a constant rate of speed. How do we apply this to things that are not? So, slope helps us measure speed / velocity. And so the question is, how do we apply this in general? Right? What if our function wasn't a straight line? What if it was doing whatever functions do? Okay? How do we map that? And the question also might arise, would such an answer be useful? Not always something that math people ask. Sometimes math people just like to chase the problem down the rabbit hole. No matter where it leads, it doesn't matter. But it is also quite useful in this sense to be able to answer such a question, because our mathematics is an abstraction, right? In other words, I could have labeled these axes whatever I wanted, right? Our graph is an abstraction. We could track virtually anything in this way. Right? So it doesn't have to be just distance over time. It could have been price versus profit. It could be size of tumor versus amount of chemo, for a little more morbid example. But you get the idea. Relabeling these axes changes the interpretation of what we're measuring, but the idea still holds true. If we can measure the slope, we can tell how one thing is changing in relation to the other, how fast one thing is moving in relation to the other. We can say, for example, that the distance is changing 50 times faster than the time is changing. Every time the time increases by 1, distance increases by 50. This is somehow giving us the ability to compare how fast two quantities are changing that are related, and we can actually tell exactly by what magnitude one is changing versus the other by measuring a slope, at least in the straight line case. I mean, this case is kind of going to be a little bit harder to get our hands on. Okay, so knowing that a graph is just an abstraction, you could have labeled these things any way we want, and the slope would indicate how the guy on the vertical axis is changing in relation to the guy on the horizontal axis. This seems, if we can somehow get this under control, we should be able to answer the rate problem for virtually any two quantities that we can actually relate to each other by some function. So now the question is, how do you actually do this? And coincidentally, I went off on a rant last class that can come in useful now. The answer is approximation. The idea is sometimes you can't know the exact answer, but you can approximate it to within any degree of accuracy that you might need. The idea is, sure, curves are not straight line, but is there some way to approximate them with a straight line? Okay. And the answer, evidently, is yes. I mean, the evidence to that answer is kind of why you have like a resurgence of flat earthers now, because on one hand, the earth is round, most of us would know that. But you know what? On the scale of a human being, it looks pretty flat, So even though the object itself has curvature, if you zoom in far enough, it starts to straighten out. That's the idea we're going to use. We know how to deal with the case of a straight line. How do we deal with the case of a curve? All you need to do is to notice, well, if we zoom in far enough on a curve, it starts to straighten out. Right? So here's the idea. Use straight lines to approximate curves. So here's a curve. Here's a point on the curve. Want to know how fast the object is moving at this point. Now, in general, that's pretty difficult. But what if somehow we could draw a line at that point that would approximate the curve? How about if we're able to draw a straight line that's going to pass through that point we care about, but touch the curve in such a way that if we were to zoom in, if we were to take that and look at it on a much larger scale, that the curve and the line will be nearly indistinguishable. That's the idea. I know how to measure speed if a function is a straight line. Just find the slope. What if it's a curve? Zoom in so that it looks like a straight line. That was the idea. What if there was a way to actually get a line to pass through a point, and then at this point, since the line and curve are approximately equal, you would define with your mathematical powers the slope of the curve to be the slope of this line. Because if you zoom in far enough, for all practical purposes, they're going to be the same. And so this is kind of one of the things that I was talking about on a macro scale. I told you guys that it's very important to pay attention to definitions, pay attention to the basic formulas, because really more complicated problems on a test are really built up of a lot of simpler problems. But on the macro scale, all of mathematics is like this. Basically, you figure out how to solve simple problems, and then you apply that knowledge to more complicated problems. Okay, we know how to deal with a straight line. Let's use that to figure out how to deal with a curve, right? And so this was the idea. Draw a straight line touching a curve in such a way that if you zoom in far enough, they are indistinguishable. So now the question is, how would you construct such a line? Now you might remember about lines, we can find the equation of a line in various ways. But you might also notice that all of these ways would require more information than we currently have. Yes, we have a point that the line passes through, but we don't have the slope. In fact, the slope is what we want to find. The slope is what we don't know. The whole problem is finding the slope. To find the equation of a line, you need a point and a slope. We don't have a slope. So now it seems like we're at a dead end, or maybe not. Because there's another way to find the equation of a line. What other information could you use to find the equation of a line? What is another piece of information that we could use to find the equation of a line? Yeah? Find another point, right? Those are the two things, sets of facts we would need to find the equation of a line. We can either have a slope and a point, or we can have 2 points, right? If we have either of these sets of data, we can find the equation of a line. Here we only have 1 point. So here's the idea. You need 2 points. But I don't care about 2 points, I care about 1 point. So here's what we're going to do. What we are going to do is take another random point. That's how we're going to start. Pick a second point. So let's say now we're on an axis. Here's our function doing as it do. Here's the point where I want to figure out how it's changing at that point. Ultimately, I want to be able to draw a straight line there that's going to approximate the curve. So this is the point we care about. However, figuring out a line that passes through that touches that 1 point without knowing the slope, impossible, can't do it. So what we do is we pick another line, pick another point. So we take some other point on the curve. And what we do is we connect those 2 points with a line. Now you might say, how is that helpful? I care about the white point. How is me knowing the white and the green point going to help me? So here's the genius of the matter. What if I make that point a variable point? In the sense that I keep this one fixed on the point that I care about, but I allow this point to move, right? What if I allow that point to move till it's right beside this one? So close that there's no practical difference between the two, right? They're right beside each other. Then, drawing a line between the 2 points would be like drawing a line between 1 point, right? So that's the idea. So here now we can start to set things up. Here's a point I care about. Let's call it x. Let's pick another point down the road. That's x plus some distance away. This distance is x plus h. Well, this distance is h, the distance between them and h. Okay? So I care about the point at x. You know what? Let's pick another point that is h units away, which would make it the point x plus h. Of course, now we can start to fill this graph out. This becomes f of x. This becomes f of x plus h. So now the idea is, I can find the equation of the line passing through these 2 points. And the idea is keep this one in one spot and move this one to there. In other words, I need to close this distance. I need to essentially make the distance between these 2 things be nothing, right? Now, do we have a mechanism for getting something close to something for all practical purposes where it might never actually be touching because we need 2 things, not 1 thing? So this point will never actually get on top of this point, but we want it to get super, super close to that point so that we can approximate things. What can we use to actually do that? What do you think? Do we have any mathematical machinery that allows us to do a move like that legally? Can we legally do it without wishful thinking? Well, how would you do it?
Take the limit.
It's a limit. That's exactly what a limit does. She's like, I know he wants me to say it. You guys are just holding out on me. That's so not fair. Like, yeah, damn you for giving us the test on the same week as everyone else. You know what? We're gonna just be silent and have you up there squirming for an answer, and we're not gonna give it to you. And she's like, I got places to go. Let's just end this. This is the limit. We know that's what you want us to say. Exactly. You take a limit, right? By taking a limit, forcing your h to approach 0, it's essentially forcing one point to move and touch the other point. Where, for practical purposes, they're the same point, but in actuality, they're not. So we know how to draw a straight line between 2 points, and more importantly, we know how to find the slope of a line between the 2 points. And so, here I'm gonna give some names to these lines. The line that we actually care about that approximates a curve at a point, this is called a tangent line. I'm not sure where that name comes from, but I think tangent means to touch. And the green line is called a secant line. So that's the name we gave them. And essentially, what we now realize we can do, we can actually find m for the secant line just by using our formula, y2 minus y1 over x2 minus x1. That would be, in this case, f of x plus h minus f of x over x plus xh minus x. X is cancelled. And so, we end up with that expression. Of course, it's the difference quotient. Right? That thing you've been doing for a couple semesters, probably not knowing what it meant. So in algebra class, they ask you to do this all the time. In pre-cal class, they ask you to do this all the time. And you're asking, what does it all mean? Who cares about this? Why that random expression? This is why. This is why they cared about that expression. It was an expression that talked about the slope of a secant line. And now we realize through the mechanism of the limit, which we've been studying for the past 3 weeks or so, we could find the slope of the tangent line simply by taking a limit. Make the distance between the 2 points approach 0 so that the 2 points effectively become 1 of this difference quotient. And that will be the slope of the tangent line. Now, some of you have taken calculus before, so I know it's anticlimactic. And some of the rest of you might have seen this expression so often before that it doesn't really evoke any emotional feeling at the moment. But that quantity, this expression, is super important. This expression gives us the power to solve the rate problem. That expression is responsible for half of calculus. It is a very important expression. It's so important that we give it a name. It is called, all together now? No, without the limit it's a difference quotient. This is called a difference quotient. This with the limit is called what? I think there was someone here who said it the first time when I asked about this. They actually said the name. It is called a derivative. And that's where the name derivatives come from, the differential calculus. Which kind of deviates from the naming conventions of math people, to be honest. Like I told you, math people are just horrible at being creative when naming something. They kind of just name it what it's about. This kind of falls into the face of that with derivative. What does that even mean? Here's a theorem that says we can always find an input to get the intermediate value. What do we call it? Intermediate value theorem. Here's a theorem that says the average rate of change is going to be the mean value for the rate of change. What do we call it? Mean value theorem. This theorem is fundamental to calculus. What do we call it? Fundamental theorem of calculus. And then someone's like, this allows us to find the slope of a curve. What do we call it? Derivative. Yeah! Put on the shades of all that like derivative. What does that mean? Why didn't you call it the slope formula? No, it's called a derivative. But it is synonymous with slope. That's what it means. The derivative is the slope. It's the slope. It's a synonym. Okay? I don't know why they decided to call it a different name, but in this case they just happen to not want to reuse the word slope. But the derivative of a function is the slope of the function at the point where it's computed. In fact, we have some notation for this expression. Now, calculus as it's studied today is largely a product of the work by Isaac Newton and Gottfried Leibniz back in the 1700s. And so the notation we use today mostly follows what they used. There is the Newton's prime notation. And this was called f prime of x. So it's not a 1, it's like a notch, like an apostrophe almost, a very bold apostrophe. And it's called f prime of x. That's why it's called the prime notation. This is called f prime of x, right? And that symbol would represent that quantity whenever you see it. You also have Leibniz's notation, and that was called dy dx, or df dx. This is if y we set to equals f of x, we can call it dy dx. This notation is extremely useful, especially if any of you would take a class like differential equations, you'll realize that this notation is extremely versatile. There are contexts in which you can literally treat it as if it were a fraction, even though technically it's not. It's a notation that means a derivative. But he puts dy over dx, and there are cases where you can literally start to like multiply by the dx's and do whatever, and literally treat it as a fraction. So it's a very convenient notation. However, these two are the main notations for the derivative. I'll mostly use this one because it's easier to write down, and I'm lazy to write on the board. It's not easy to be doing this all the time. So I'll mostly use the prime notation, but if you see one or the other, you should notice that they're the same thing. There are other notations for them, but these are by far the most common in Calculus 1. And so with that, we can actually state a definition. So yeah, we solved the rate problem pretty quickly, but that's because we've known how to do it for centuries. Technically millennia, if you really want to be honest about it. So I could summarize very quickly, but it took a lot of painstaking thought to actually be able to figure this out. It took centuries for us to figure out there's a number 0. You know, some thoughts, they seem obvious in hindsight, but they weren't at all obvious when they were being developed. A lot of work went into doing what we did here today. But right now we can state it as a definition. Let f of x be a function the derivative of f of x with respect to x. That's just talking about the fact that we're always relating one function to another. We're relating the y value to the x value. We're relating the quantity being tracked on the vertical axis to the quantity being tracked on the horizontal axis. So we're always talking, how fast is this changing in relation to that? How fast is this moving with respect to that? So the derivative of f of x with respect to x, if it exists, it might not exist, because it's a limit. Limits might not exist. We've actually already talked about that. So the derivative is not something that we'll always be able to find, and I'll talk about specific examples where we can't find it. But the derivative of a function with respect to its input value, if it exists, is given by f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. We call this quantity the derivative. So on future quizzes, probably a test, I will sometimes specifically ask you to define a derivative. Whenever I ask you to define a derivative, I expect you to write this down. And I expect you to write this equation down in its entirety, not just the right side, not just the difference quotient part, the entire equation in its entirety. You need to write f prime equals this limit, or you need to write dy dx equals this limit. You need to memorize the entire equation. Whenever you memorize a rule or an equation, you memorize it in its entirety. Memorizing one side of things is going to get you in trouble, starting pretty soon, actually. So this quantity, super important, solve the rate problem. It is called the derivative, and as the definition suggests, it might not exist. But if it does exist, it actually allows us to solve various problems, the interpretations. So there are times in this class where you might need to find a derivative. You want to know when these times are. So it makes sense to actually talk about what this thing actually means. So here are some interpretations. The first basic one is the geometrical interpretation. This is the slope of the tangent line. At x. That's your first geometrical interpretation. That's essentially what we wanted to do. Was the slope of that pink line that approximated a curve. We can also talk about it as the slope of a function. Because the idea is if you zoom in far enough, the tangent line and the function are going to be doing effectively the same thing. They can approximate each other. So you can think of it as the slope of the tangent line or the slope of the function itself. You can think of that as the rate of change of f with respect to x. That is the speed at which f of x is changing. So the mathematical interpretations are slope of a tangent line, slope of a function. More real-world interpretation of a derivative is just measuring how fast something is changing. Okay? So if there's ever a context where you need to measure, you're given some function or some quantity that you're tracking, you want to know how fast is this thing actually moving in relation to this quantity. You would take the derivative of that thing with respect to that quantity. That's essentially the idea. That's the solution to the rate problem. So derivative is just a synonym for slope, in particular slope of the tangent line. Tangent lines are useful because they approximate functions at a point, and the slope of the tangent line is considered equal to the slope of the function at that point. Let's do some examples. Say I gave you the function x squared, very typical first example to use because it's pretty easy to apply, but at the same time it's not stupidly trivial. So the question here is, let's find the derivative of the function y equals x squared. As I suggest, if it's been a while since you've seen this formula or you've never seen the formula before, you really want to have this formula burned into your brain. So you really want to write it down pretty much every time you're going to use it. So obviously, start by writing this expression, limit as h approaches 0, of f of x plus h minus f of x all over h. And what would that be here? Okay, what is f of x plus h for this function?
X squared plus
Minus?
x squared over h.
Is that right?
No.
No. Did the same person that say that say
Well,
no?
I mean, they're shaking their heads, so it's like, I don't know.
No, that's not right. What's the problem? Yeah,
Isn't it x squared plus 2xh plus h squared minus x squared?
where did that come from? Where did all that come from?
Because you have to plug the x plus h into the x.
Okay, remember how functions work. What's in the parentheses is that quantity replaces x everywhere. So what this is, it's f of x plus h on the end. No, you want f of x plus h, right? So literally x plus h replaces the x in the definition of the function. Don't forget how functions work. Okay, so that is going to, and at this point, we've been spending so long with limits like this should be easy for us. This is just going to expand. H's are going to cancel. Ultimately, we want to be able to plug in h equals 0 if possible through simplification. Here, oh, we can just cancel h here, right? Right?
You should pull it out first.
You need to factor it out because you can't cancel across sums. do that in Jhevon will kill you. Factor it out, now we can cancel. So now we end up with a limit of 2x plus h. Factor it out, be 2x plus h left over. And now we can actually plug in h equals 0, we get 2x. i.e., if f of x equals x squared, then f prime of x equals 2x. There's another notation I want to introduce to be able to say this because I don't want to have to write that sentence out all the time. You can actually use Leibniz notation. Remember how I told you it was very versatile? You can think of something like dy dx as d over dx times the y. You can kind of shift this off just like you would in a fraction. And so we can talk about, this would mean the derivative, this by itself means the derivative with respect to x. It's called a mathematical operator because it needs to have something beside it to work on. So you can actually shift off that notation and write it that way. So another way to actually say that entire sentence in one short mathematical equation, you could actually say d dx of x squared, where the x squared is replacing the y, is equal to 2x. Right? That is saying the same thing. Okay? So it's saying the derivative with respect to x of x squared is 2x. That's what you're saying by when you write that equation down. To make things a little bit more concise, we can sometimes use the Leibniz notation. Now, what does that mean? Well, it means at any point x, the slope of the function y equals x squared is given by 2x. In other words, tell me the location we're at and I can tell you the slope of the tangent line to that location. Example. If x equals 2, then f prime of 2 would be 2 times 2 equals 4. And what you can think of that number, how you can interpret that number, this is the m for the tangent line. So, for example, someone could ask you a question like this. Find the equation of the tangent line. To y equals x squared at the point x equals 2. Now what you would do at this point is you would say, well, since y prime is equal to 2x, using the Newton's notation, this means that m for our tangent line is just going to be that function evaluated at 2, which is 4. So that's the slope of your line. We can now know point on the line is going to be, well, 2 comma 4, because it's y equals x squared. This means y minus y1 equals m x minus x1 is going to be the equation of the tangent line. We could say something like, if you want to, that's fine for me, but if you want to write it out in y equals mx plus b form, That would be a -8, add 4, square is -4 would be how you can write it. But the interpretation still stands. Graphically, this is what's happening. You have the function y equals x squared. You locate a point 2, where that's here. The output is 4. And so someone would ask, well, if we were to draw a tangent line there, what would be the equation of this line? Well, the equation of that line is going to be y equals 4x minus 4. So it's going to pass through the point 4 here, minus 4. The slope will be positive 4. And the idea being, if we zoom in close enough to this region here that contains this point, the curve of y equals x squared and the line y equals 4x minus 4 will effectively be doing exactly the same thing. One can be used to approximate the other. Yeah.
Do you expect to see that work once we get more comfortable with this? Or if we can look at x squared and know it's 2x because you move the 2 down and subtract 1 from the exponent?
You'll definitely be expected to do this. I will specifically ask you to do this. So whenever you know to do this, the question will be phrased like, use the definition of the derivative to find.
Okay, but if you
y
don't
prime.
say that, if you're just like, what's the derivative of x squared?
Yeah.
You can just write down 2x.
Yeah,
Perfect.
so definitely on the first test you'll do both. Probably on the second test I won't ask you about this.
Okay.
But it's definitely something that we expect you to be able to actually work out. Eventually the functions we want to be able to deal with are going to be just way too complicated to go through this. But I'm going to ask you simple, like a polynomial or 1 over x or any of that. Find the derivative at that point using the definition, or use limits to find the derivative. Use the definition to find the derivative. Things like that.
Okay.
If I just say, find the derivative of the following, then do whatever. Do the shortcut. You want to do this, you can, but it's not required.
Okay.
But whenever the problem would say, use the definition. Yeah. But yes, eventually y equals x squared is something you should be able to just do. But yes, the computing limits via the difference quotient, the limit of the difference quotient, is something that we'll want to test that you actually know how to do for historical reasons. The thing is, a lot of the functions we're doing in this class, we'll have shortcuts for them, but at the end of the day, there are some problems, some functions that are just so nasty, we don't have a nice formula for them. And this way is the way you would go about computing those. So we still want you to have some idea of how something like that might work. So with that, we'll stop there. We'll do a lot more computations with derivatives. And like I said, we'll develop some formulas that makes doing this a lot easier. Until then, I'll see you guys on Tuesday.